All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying on this one, let's determine the internal reactions, our normal force, shear force, and bending moment at point D on our frame that we have here. So if we're doing this, I'm going to need to make a free body diagram that slices through point D. I'm going to have to assume or use the positive sign convention for normal, shear, and moment. We have those written out here just because we'll keep referencing them. And we'll talk through that in a bit. But I'll have to figure out, how do I make that section? I know I'm going to slice through D. So if I cut through right here at point D, I could set up my free body diagram to go from D around B through C and close out a free body diagram. Would be a valid option for us. If I did that, I need to know CX and CY. I could go from D and cut through B. That way I need to know BX and BY. Or I could go from D and go around through A. I need to find AX and AY. Either way, there's two reactions I need to know in here. I'm going to try to circle around to the right or to the left on this. Kind of set up this free body diagram circle. Cutting through from A over to D. I'll have to include 1 meter's worth of distributed load in here, and everything else I'll cut away from that. But again, to do that, I need to find my pin, AX and AY, in here. So let's start out there before we even talk through our sign convention for this. So if I'm just trying to find AX and AY, could I work with an overall free body diagram and find those? Well, I would have AX, AY, CX, CY. 4 unknowns, I wouldn't be able to get all of those from that overall free body diagram of the frame. But if I drew that out and I sum moments at C, I would be able to get AX in there. So let's actually start at that point. So I'm going to come in and make a real quick free body diagram. Our entire frame looks something kind of like this. My height in here this is 1.5 meters tall. At C, I should have a CY, and a CX. And up at A, I should have an AX and an AY. So I'll put that going up, AY, and to the right, AX. Along the entire top of this, there's a rectangular distributed load. So we'll show that going down. And it has a height of, 250 newtons per meter. So we'll get that in there as well. 250 newtons per meter. And then the width of this is just 4 meters. 4 meters wide. And then finally on the right edge there is a triangular distributed load. Let's label that as well. It gets to a maximum height here of 300 newtons per meter. So we'll go ahead and label that as well. All I'm looking for on this, I can either get, I want to find AX and AY. AY would pass through C. There's no way I can find this with the overall free body diagram. I could come in though in some moments about point C, and I get AX out from that. So let's start there. With positive going counterclockwise. Positive is counterclockwise. Let's sum up our moments about point C. If I'm doing that, I'm going to get a clockwise rotation from AX. So negative 1.5 AX. Negative 1.5 AX. Force is AX, distance is 1.5. My rectangular distributed load would cause a clockwise rotation. So minus our force for a distributed load is the area. So base times height, the area of a rectangle. 4 times 250. That's our area. I need a distance from C to the midpoint of that rectangle, on which that rectangle starts directly above C, so it's just half of the width of that, times 4 over 2, or times 2 would be my distance. Halfway from C or A to the midpoint is half the width of that rectangle. Finally, my triangle will cause a clockwise or counterclockwise rotation, so this is positive, plus force is still area, so 1/2 base times height. 1/2, 1.5 times 300 is, again, just force. I need force times distance, which distance for a triangular distributed load goes from the 90-degree angle in it, so from right here, 1/3 of the way into the triangle. That 90-degree angle aligns with point C, so from C up, it's just 1/3 of 0.5, or 1/3 of 1.5, which is 0.5. And that's going to get us to 0. If I solve that for AX, I'm going to get a negative number here. AX is negative 1258 newtons. That was negative when I assumed it went to the right in here. That negative, though, tells me it's really going to the left. So let's report that AX is really 1258 newtons going to the left. Now I'm going to come back here and put in a dashed arrow just to help me remember that. It's really going to the left in here. That solid one is what did I originally assume. The dashed is what's it really doing if it's different than my solid arrow in here. But then we can keep going with that. Is there any value in me getting CX on this? I don't need CX in here. Let's just skip over it and keep going. So we'll make a new free body diagram. What if I drew just AB? Well, now I know AX. I would have unknowns of AY, BX, AY, BX, and BY. Three unknowns. AX is known, so it's not an unknown for us. But I could tell all I need is AY. If I'm circling to the left up here, AX and AY need to be found. If I just sum moments at B on a free body diagram of AB, I'd be able to find AY. So let's just go there. So we can come in and get another free body diagram drawn. We have our horizontal beam, has a rectangular distributed load coming down off of it. The height of this is 250 newtons per meter. 250 newtons per meter. At A, I should match what I either assumed or found already. So we'll put AY going straight up, and let's put AX going to the left. And I know its value is 1258. So we'll put it as a known, 1258. Over here at B, I haven't assumed anything. They're not actually going to end up mattering for us because I'm going to have some moments right here, but I should still show them in my free body diagram. So I'm going to put in a BY and a BX. And my width here is 4 meters. So let's just sum moments here at B, and I'm going to get AY out for that. So I'll come up here with positive, going counterclockwise. Let's sum up my moments about point B this time on a new free body diagram. My rectangular distributed load will cause a counterclockwise rotation, a positive moment here. So I need base times height, the area, 4 times 250, times the distance from B to the middle of that rectangle, should be 2 meters. And AY will cause a clockwise rotation. So minus 4AY is going to get us to 0. Or if I solve that out for AY, I should get here that AY is 500 newtons. And we're going straight up, which is my second support that I need really to be able to set up this free body diagram. So I have everything I need to go into kind of new material on this. Everything up to this is kind of just a review of rigid body equilibrium. How do we do frames? How do we do distributed loads? Our new step would be we're slicing through right at point D and making a new free body diagram out for this. So if I came in and I drew this, I would have in here, we're going to go from A over to point D. And I always draw a wiggly line to help me remember that's right where I cut this at. So I'm cutting this at, this is point D. We'll even label that in there. This is D. My distance from A to D is given as 2 meters. So there's a 2 meter distance. At A, I have my support reactions. I found AY was 500 going up, so we can get that one in there, 500. I found AX was 1258 to the left, so we'll get that one in there. 1, 2, 5, 8. And then I can stick, I have 2 meters of a distributed load. Always reapply this as a distributed load. If you're in the habit of taking distributed loads and showing it as a single concentrated force, that's going to become problematic here. We don't want to do that on here. We want to reapply our distributed load. So I have the same height on this, but my distance has changed. I'm not applying this over 4 meters, just over a 2 meter distance. But my height is still 250 newtons per meter. And then the last thing that I get in here, right where I cut that, internally holding my beam together, I have internal normal force, shear force, and moment. So I have to get all of those in here. Normal force, we will always assume this because there's a standard sign convention for it that says normal force is positive when it puts our object in tension. So we're always just going to put this in tension. So that would be acting away from point D. I have a normal force here. Let's call that ND, the normal force at point D. I can come in and do the same thing for my shear. Shear is positive when it causes a clockwise rotation about the uncut end of our section. So that would be if my cut's right here, the uncut end is point A. To get a clockwise rotation, my shear would have to go down. So I'll put my shear going down right here, VD. And my moment compresses the top section, or the top of whatever our section. We have section AD here. That was a little bit tricky. I kind of explained this. If you think of you're holding your hands together like this, if I try to bend, so either direction in here, if I bend and lift my elbows up, really I'm putting a counterclockwise moment on this. My thumbs at the bottom spread apart. If you're thinking through what's happening on any material, if it's starting to pull itself apart, it's in tension down there on the bottom. But at the same time, my fingers up on the top are starting to squish into each other. They're compressing in. That's putting my fingers into compression when I have that counterclockwise moment on the left edge, or that's the right edge of my hand. We can really look at the picture too. Or if it's on, my cut is on the left edge, then a clockwise rotation, now we'd be looking at this piece of my hand clockwise, would be squeezing up on the top, pulling apart my thumbs down below. I mean, we'll always set this up using our positive sign convention. So I need to get a moment in here, MD, that's going counterclockwise on this. Normal force, shear force, and moment, all set up with just that standard sign convention. These matter for us to get right, because where we're going to go with this down the road is, rather than just looking at what's happening at point D, we're going to come in and say, what's happening everywhere in here, from A all the way out to B. We're going to make a plot of that. Where's our shear? Where's our normal force? What's our moment doing? We can sort that out, but to talk through and make a valid plot, I need to know what's positive and what's negative. That will matter a lot more in mechanics and materials then when we start dealing with like stresses. And we have stresses coming from various things, like a bending stress or a shear stress, and we're combining that with other things that cause similar stresses. How do we add those together if we don't have the signs right? We got to get this right. Figure that out early. But this will be our sign convention we use for this. But really, I have three unknowns in here. I can find everything. So let's come back up above, and I can just say, let's start by, why don't I sum my forces in the X? Summing forces in the X. I have ND going to the right. I have AX going to the left. Minus 1258 is going to get us to 0. Or that normal force, ND, is equal to 1258 newtons. Because we have a standard sign convention, I'm not going to put an arrow or say like on a section, anything like that. We can just leave it as is. And move on to the next one. I could sum forces in the Y direction. Would get me, I have 500 going up, minus the area of my distributed load, base times height, 2 times 250, minus the shear, minus VD equals 0. If I solve for VD, I'm going to get that there's no shear right here. VD equals 0. That's going to become a really important point for us, because anywhere that our shear is 0, our moment's going to be at a local max or min point for us. 0 shear goes to maximum moment. If we're designing things, that matters. Let's come in and find MD. So I'm going to say with positive going counterclockwise, let's sum up our moments about point D. As I do that, I have my internal moment, MD, going counterclockwise. My 500 will cause a clockwise rotation, so minus 500 times 2, force times distance. My distributed load will cause a counterclockwise rotation. So plus area, 250 times 2, base times height, times the distance from D to the middle of that rectangle is half of 2, or just times 1. Should get me all the way to 0, which I can solve that for MD. I'm going to get that moment about point D should be, or our internal moment at point D is 500 Newton meters. And again, because we have a standard sign convention that's just commonly used in industry, we're going to go with that and say, I don't need to put in a counterclockwise or a clockwise arrow on these. Just leave it as is. Don't drop a sign. Just leave it exactly what your equation solves out to be. But hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Stick around. Let's get you in A with JJ.